In our last video, you were introduced to angular momentum, in particular, the angular momentum of a point mass. And we saw the angular momentum of a point mass in magnitude is mv, which is the way you calculate linear momentum, multiplied by a perpendicular component to a lever arm. So that came from a more general vector equation that says angular momentum is a cross product of lever arm and linear momentum. Okay, well in this video we're going to talk about angular momentum of a rigid body. So let's picture a large rotating disc like a flywheel. Actually, you see less and less of these days, but I can remember as a child just about every neighborhood park had a large, what do we call these? Is it a merry-go-round or not a carousel? I'm not sure what we called it. So I don't know if you had these in your neighborhood park when you were younger or not, but there was just a, just a big sand pit, and then this thing was, I guess, buried into the ground on a large axle, and it was free to rotate. And it took some effort, and kids would stand here and hold on to the bars. Some kids would sit down. Some would sit near the axis of rotation. Some would try to stand near the edge. Regardless, everybody on board shared a common angular velocity, because angular velocity is measured in radians per second, and angular velocity is independent of how far you're standing from the axis of rotation. Well, invariably, it would spin too fast and people would fly off, and I think there are a lot of injuries associated with these, so they've become less and less common. So let's take a bird's eye view of one of these large merry-go-rounds. Okay, so right there at the center is our axis of rotation. And we could break this thing up into a bunch of little tiny point masses. So if the whole rotating disk has a mass capital M, there's a little bit of the overall mass dm. Now that dm sits at a distance of r, whereas this one sits at a different distance of r. So there's an r1 for dm number 1, there's an r2 for dm number 2. Maybe you've got one that sits really close to the axis of rotation. That one's got an r number 3. Well, the one thing that's the same, even though all these dm have different locations relative to the axis, they all have the same value of omega. Every one of them spins with a common number of radians per second. Now, as far as their linear velocities or tangential velocity, dm number 1 has a large velocity vector that points tangent to its circular path. dm number 2 travels in a circular path of less radius and has a tangential velocity. And then the third dm that I've shown here has an even smaller radius and therefore an even smaller tangential velocity. Well, the total angular momentum should just be the sum of all of each one of these dm's contribution to the angular momentum. So the total angular momentum should be the integral of what? dm times v, so that's the linear momentum part of the equation, and then times r. That's it, right? Angular momentum is mass times velocity times perpendicular lever arm. Okay, well, we can substitute in place of v omega times r. I'm not sure I really need to break the lever arm into parallel and perpendicular components. In all these cases, the lever arm is exactly perpendicular to the linear momentum. When I multiply dm times v, I get dp. So when I multiply dp times its lever arm times the sine of 90 degrees, that gives me this expression. All right, so the angular momentum of the whole rigid body, the whole system, is the integral of omega r replaces v, then we got another r, so it's omega r squared, then all of that multiplied by dm. But remember, they all have the same value of omega, so that's a constant. It comes in front of the integral sign, and we're left with angular momentum of the system is equal to omega times the integral of r squared dm. Now I hope you recognize this. You see it? Sure. The integral of r squared dm is our definition of rotational inertia. So what we find is for a rigid body, angular momentum is equal to I omega. Now isn't that interesting? When you look at all of the analogous equations, so what's an analogous equation? Translational kinetic energy is 1/2 mv squared. Rotational kinetic energy is 1/2 I omega squared. Or how about an analogous equation for kinematics? V equals V naught plus AT, omega equals omega naught plus alpha t. Or what about force? Sum of all force equals mass times acceleration. Sum of all torque equals rotational inertia times alpha. So do you see it? We just derived an equation that says angular momentum for a rigid body is I omega. That looks very analogous to linear momentum is mass times velocity.